All right, everyone, I think we're good to get started now. Welcome to the Open Source Showcase. My name is Lenore. I'm one of the community leads here in GDG. My name is Erica. I'm the other community at GDG as well. Yeah, and as you guys know, open source teams have been working really hard this entire year to create some really cool projects. And really glad that you guys have been here to join us today to highlight all the work done throughout this year. So to start off, again, we'll be going with our project photos. So we have to have the board first, and then glass box of, and then in that. We will then end off with some pizza, some GDG, and as well as the net. All right, so with that, I'm going to pass it off to Harrison and his team to showcase their work organization. I can have mine's on.
Okay. Hopefully everyone can hear me okay. My name is Harrison. I'm the lead of the core board project. Here's some of the other team members who worked on it with me. And then I'll just get started. So our agenda for we're going to cover our motivation and goals for the project. We'll go over a project demo, go over our key achievements for each sub-team, and then we'll talk about the next steps of the project. So to start with, Corkboard is. Corkboard is a mobile-first full-stack application designed to help students or anyone interact with local music. So it's built with an industry-relevant tech stack, which was React, Tailwind, Supabase, Express.js, and Jest. And it provides views that give users access to local shows at small venues, user-submitted venues, or bigger venues like the TD Coliseum. So the app was built to be scalable so that it can continually develop over time and add new focused features, expand geographically down Hamilton, and support new events in the community. So some of the goals we had for the project going into it was for all the team members to learn new tools and gain relevant experience. Since we're building a full stack mobile app, there's the front end side, the back end side, which we also further broke down the database streaming, which can be used to strengthen their portfolios and help them in the future when it comes to working in an industry career or application. And then, yeah, we wanted to make sure that they have improved experience with industry relevant tools and transferable skills when it came to development and design of a project like this. And then also we had a focus on using collaborative practices. So we had a Kanban board set up with a bunch of different tickets so that we can each take tickets and allocate our work that way, like similar to an actual industry setup. And then finally, there was a lot of interconnected collaboration between the sub-teams that we broke up. So our team members weren't exclusively working on just one aspect of the project. They would work with each other on various different ones.
So we presented this last semester at the semester part of like the open source showcase. Since then, We've allowed users to submit event drafts, and those are reviewed on our new admin dashboard for the go live. We have the user account page to customize favorite genres for the user and then the menus. You can add a bio and a profile picture. Hopefully one day we'll have like social networking so you can find people that are into the same music as you. We have login registration to complete our entire auth flow. Most of the API endpoints that need to be are authorization oriented. So you need to pass in the right tokens to get the features. We have more web scraping, so you pull in events from more venues to grow the platform. And we just optimize and fine tune more of the system architecture.
Okay, so now we'll project. So I'll stream that in. Okay, so I think, yeah, everyone can see that. It is a mobile first app. So first thing I'm going to do is get an account to use the app. Come up with a name. And an email address. And add an uppercase letter. Okay, so now I have the account. And this is the Explorer page of the app. So we can see some of the personalized events for us. Of course, we just made an account. So we need to actually personalize it to our needs. So we can add some of our favorite genres for the app. Just find events that we're interested in, like rock or jazz. And we can also specify what some of our favorite venues are in Hamilton. For example, Mills Harbor. We can also customize, for example, our profile picture or our bio. And then now when we go to the Explore page, we have events that are actually personalized based on our favorite our favorite genres and venues that we selected. And we see personalized events for us, events based explicitly on our favorites. Some of the featured events in Hamilton, like the Google Dolls performing tonight. And we can select one of these events to see more information about it. And if we're planning on attending an event, we can bookmark this event, save it for later, which we can then see at the top of the Explore page. And we can click the button that should be redirected to the ticket page to actually buy tickets for the event. You can also see more events at this venue in particular coming up. Visit that venue site, and I can favorite that venue. We'll add it to our profiles favorite. We also have a list-based feed for events where we can search for events by genre or venue, specify start and end dates for the events we're looking for, and adjust the ticket price. Similarly, we do the same level of filtering on the map data, which is more location-based, so you can look specifically for events in the year. And if there's multiple events at the same location, we can just see the actual venue itself and look at all those events that are happening. So now, as a user, we're also able to submit events. So it's not just events from the venues themselves. We can have users submit events for example, local shows, house shows. For this example, I do showcase. Select the date, be tomorrow. Adjust the ticket price. I will select an existing event for this event to be at. We can create a new one. Just say Hamilton Place. And then the part, which I'll just say has started. And then submit that event. Now, as an admin, we've also created a admin dashboard so we can manage all the events within the database and handle user-submitted events. So here's the showcase event that I just created. I can see all the detail about it, the information about the user that submitted the event, venue information, artist information. I can reject this event, I can edit its information, or I can publish an event and now see it if I all the events as part of the listed events on the app. And now if I actually go to the show and search, it should be, or should, maybe it hasn't been loaded yet, but it will be there. It might just take a minute for the database to reload. Okay, I think that's pretty much anything. I think I missed anything. Okay. So that's a quick demo on what the project actually looks like and what it would be like for a user and for an admin handling the project. I'll go back to the presentation now.
Yeah, so a little bit about the project architecture and how this is all going down. So essentially we have an Express database, or not Express database, Express server, sort of sitting in the middle of everything, kind of acting like a common interface for the database, because the project really revolves around the database. It's all about the event data, the user data, the event data. That's all it's all about that. So we created a sort of standardized interface through Express server. So we can see at the top, the scraper will send data to the database through the Express server, to request the Express server, and then the Express server will communicate with the Supabase database. And then anytime a user wants to see new events or wants to update the profile, they're going to send a request to that Express server, and those requests are going to be passed on the Supabase database, and then it's going to propagate back that the request was sent successfully. So on the side here, you can't really read anything; it's kind of blurred. But this is the database schema. You can see it's very complex. There's a lot of different tables. I think this is like user submitted events, and then some of these are like favorites. So there's some many relations, some one-to-one relations. You can see all the foreign key relations flying all over the place. And then at the top, we have a beautiful UML diagram of all the classes that you can read very clearly. But yeah, that's sort of the whole project architecture of Workboard.
All right, so on the front end, the tools we use throughout this project are Figma to do the initial designs of the app. And then for programming it, we used React Native and then Expo Go, as you saw in the emulator. That's what we use to actually run the app on the phone. And then we just focused on building a clean and intuitive UI and always thinking about the user first and what's going to make their experience like smooth and simple. So we also focused on making it easy to navigate. Like we have the different page tabs at the bottom, for example, to easily switch pages. And then we also had the smooth login and an account page, and overall just making sure from the login page, the user can easily find their way around the app. And then we also got the search and the filtering working. Like as you saw on the event page, the user can pick any filters they want to use to look through the events. They don't have to use all of them. If they care more about the ticket price or want to start and end dates, they can pick and choose what they want to filter with.
Yeah, and then we also integrated the front end with the back end APIs to handle data. And we learned that front end development takes a lot of iteration. You don't get everything right on the first try, and then tweaking based on what your user needs might be. And then based off of that, changing small things as you go makes a big difference. We gained some experience managing state and API data and just improving our debugging skills as you're adding things go wrong and you want to like balance moving forward with fixing things. Yeah.
Okay, so for the back end, as I mentioned before, we implemented an Express server, and we implemented this as a RESTful API to integrate with the Supabase database. And with Express and Jest, we were able to create and test 40 plus endpoints, which is probably too many, but it's fine. And then we used Supabase to support the relational data storage, and then Along with that, we had image sort, which is like using data buckets, I think. And then authentication as well, which is sort of a perk that Supabase gives you. And then the main thing that we were able to do, kind of big achievement, was creating that data flow pipeline from the scrapers to the user through the Express in the database. Yeah, so we were able to create an efficient way for data to propagate from different venues and able to get it into the database and to the users so that they can actually do stuff with them via the events. And yeah, so we really learned like a lot about how to effectively design, build, test, and document like a large scale project. You saw the UML diagram, it's kind of like crazy, people adding stuff, and you have to like, it's really a big learning experience on how to manage something when you have a bunch of people adding to such a large complex system, especially with the documentation. When you make the documentation and then move where it is, you should probably tell people that. And yeah, we also created an admin dashboard for approving the events and making sure that no bad events get onto the database.
Okay, now moving on to our conclusion and the next steps for going forward. Okay, so for what's next for Forward, we want to prepare the app for getting new deployment on app stores. And part of doing that is adding more venues to the apps. We have a lot of the venues that are in the asset right now, but there's still some product we can do. And we want to be able to support a broader range of devices. So it's not just the newest devices that you can emulators. Right now, it's mostly Android, so moving to iOS support, and then just making sure it's still optimized and able to support very different screen sizes. So there's a QR code here for the actual project repo itself, and this is an open source project. It requires accepting or any work on the project. We have in their board, which I believe is public, if you want to work on tickets. But in the future, we're just mostly preparing for multi-deployment as the next stage of the app. So now we'll take any questions if there are any. Yeah.
So are you guys going to support this like along like a time period? And if so, like how long are you going to support the app for? Or is this just like the final project?
Well, we're going to continue working on the app, and we're moving to mobile deployment. So we want to keep supporting it for a while and try to promote a user base. But if if the user base is successful, obviously we're going to keep supporting it over time. But like it's set to recheck all the data websites for a bunch of new event data at the time. So it should still be functional, even if we don't do it for a time. Yeah.
Is the admin page only accessible to you guys?
Yeah, the admin page is only accessible to us because there are in the .env file, like having keys that you only have as an actual developer. So if you want a project, you're not going to be able to just run the admin dashboard locally and edit all the events. Yeah.
Sorry if you're being repeated, but what difficulties did you encounter when you were trying to scrape websites and your
Yeah. So some websites are like some venues have very basic websites, like schools or whatever, and they don't really have any bot detection. So it's really easy to scrape the HTML from that. But there are some like Ticket Web, a lot of venues where they have a lot more information that have like bot detection that they can be difficult to get around. I don't know if anyone else who did bug treatment wants to talk about this.
And there's a lot of problems with like modern websites being server-side rendered, especially on some of the bigger platforms. Ways to get around that were just like using packages like Selenium to actually emulate a browser rather than just like calling a curl and then parsing the HTML.
Okay. Because if there's no more questions, then we can go on to the next demo. So, thanks for having us.
Great, thank you guys so much for that demo. Let me check. you guys so much for that demo. So now we'll be moving on to the Glassbox.
So yours is which one?
Fourth one. I think it should take like should be
Number
on
4?
the fourth.
I'll just grab the computer. It's okay. That'll be easier.
Yeah, it's just that when I ran yours, it like took up the entire time.
Yeah, mine will
But
take
it's
time
okay.
to run too. So it'll save some time if I just.
Yeah.
Can you start it up now so then
I'm just gonna mute my computer. Yeah, it's done.
Yeah.
Oh, it's
Awesome,
done?
thank you.
Set up on it.
Can you join the call? The stage? It's in the.
Oh, so I'm just gonna screen share. Okay.
Yeah, exactly. That's how you.
Um,
Okay. Do you have the link for it? I can just send it right now. Oh, you have it. Okay, cool. So whose demo do I need to show? Yours, and then everybody else has theirs on.
Just this. That's all.
Okay, cool. Yours is good here. Okay.
Mine is good?
Yours is good. Is yours here?
Yeah, I mean. Are you gonna
Your days is also here.
I think.
Sorry. On your laptop. Okay. As long as you guys are all on the call, then we can just switch around. 'Cause-
So should I just join the meeting?
Yeah. And then Erin.
Oh, do I have to join?
The stage, just like whoever shares screen has to. And I think to make it easier, you guys should just all join the stage.
Yeah, I'm gonna get
Like try to.
I think I just need to.
You have to click this.
Oh, this? Press this week?
Actually, click this one. Is there a?
You might have to be like let in to do it. I don't know if you can like. I think request to speak should be.
It should be. You should have a button that's like join the stage.
That's probably only because you've already done it, right? They probably have to let him in.
Can you let him?
Can you let him in? Like if he raises his hand, can you?
It's just to speak. It's
Can
not
you
to.
see?
It's not to
How do you
join the
enjoy
stage.
this?
Wait, let me see.
How does the?
It's just like it's in the Discord. Yeah, that's what.
Oh. But that's just to speak. Is
Yeah,
that
I don't think
to?
that's
Okay.
You can share screen. Okay. Everybody request to speak, and then we should be good.
Request to speak. Just request to speak. They'll.
And then I'll accept everybody. Okay, nice. Okay.
Just making sure that
It's just the issue is the computation. It crashes the notebook
oh, really?
every time I run everybody's
Oh,
experiment.
shit.
Just because of the amount of data, but it's okay. We're good. So you're first,
I'm
right?
first.
And then you're second. Anybody else know their order? Yes. Let me do that. Share my screen. Okay, we're good to join. Everybody's.
I can screen share 2 videos, right?
Yeah. You just have to select that's your entire screen. You can just do it.
Does everyone let in?
I think so, yeah. Okay.
You guys are let in?
Yeah, I'm not in.
You got it.
Unless you requested to speak, you're like off.
Or should you remove
Someone
someone?
has to like stop it.
Muted my bad.
Oh yeah, it's because one
Oh,
person's sharing.
okay.
If she
Okay,
unshares,
we
she
good.
shares.
I gotta request to speak as well.
So when we're on.
You have to request to speak. Are you in?
I just requested.
Okay, let me just admit you. Here, I got him. Yeah. You're good. Okay. Sorry for the delay. Okay. So, we'll have like the speakers stand kind of here. The stream is right here. So, sorry for the delay, guys. We're Glassbox LLMs. My name is Rowan. I'm the lead for this team. And so we're just gonna get into the motivation goals. So our project is called Glassbox LLMs. It's a research-oriented project, so you're not going to see a pretty user interface, unfortunately. So our project was focused on, or inspired by, rather, by Anthropic's recent research on the biology of large language models, which is basically interpretability research. This is kind of dated now because the large language model research field moves so quickly. But when we started, this was like fresh, 8 months ago. So we kind of based our modules and our research structure off of their, it's kind of like a research series, so they have a couple of modules for each section. And so that's what we based it off of. And its focus is trying to dissect the black box nature of large language models and kind of explain their behavior, trying to like kind of dissect them as if they're human brains and figuring out which sections do what. And so some of our goals as a team were to apply some hands-on interpretability techniques, and we hoped eventually to publish our findings as a open source repository. So getting into more of our goals, initially the beginning of the project was to do a lot of literature reviews and get, again, with that Anthropic research series. And so just trying to get into that bleeding edge research, and then trying to apply those hot skills into like real life applications with large language models and getting some of that hands-on skills. So we're just gonna jump straight into the demo. I think we can swap over to Yudo's screen. So just a bit of background, our project, we published it as a pip library, so you can pip install and run all the experiments that we went through. The target users are, yep, I have to stop screen, okay. So our target users are kind of researchers and students rather than industry right now, but eventually that's like the goal of the project. So we have a couple of experiments that we're going to showcase. It's kind of going to be all over the place because our experiments are really heavy to run. So if we run them on a single Colab notebook, it'll kind of crash. So we're going to jump around between a couple of different laptops. And I think you have to switch to...
Yeah, so we can start with our first thing that we added to this library, which is linear probing. So what is linear probing? So linear probe is just like a small linear model. We're using rich regression. And what it does is it trains on transformers like frozen internal activation. So we're looking at the frozen activations of an LLM, and we're trying to train a model on it, and then trying to see if there's like stuff like if a statement is positive or a statement is negative, that stuff is like linearly encoded in the activation at that point. Because if you're just looking at the activation by itself, you can't really tell what type of information is encoded. So with our library, you can just do this in like a couple of lines because we have an activation store class and then we have a linear probe class that you can just use to like train the linear probe and easily get the activations from any type of transformer model. So first we have the trained data, which is like labeled. And as you can see, like, so right now we're just using like positive statements are like scored closer to 1 and negative statements are like scored closer to 0. So we're training we're passing this data through LLM and then we're stocking and getting the activations from like any layer that you pass in. So, and we also have the test data, which you're going to see like, on which we're going to test the linear probe on. So here we're just, so we're just going through all the layers here, and you can simply just do store.extract, which is going to call our classes, which are implemented in our Glassbox library, where you can just pass in the training text, tokenizer, any layer, and then the type of queuing you want to do. And then here's the linear probe class, as you can see. Here you're just going to pass the layer, the direction, the model type, and then normalize, and the regularization. And you can just do probe.fit to like start training the linear probe. And once we run it, we see that the first layer, H.0, is like where we get the highest R-squared value. So we're going to use that to train our linear probe on. And here is just like some visualization. And as you can see, layer 0 has the highest R-squared value. So we're going to use that layer. So we retrain our linear probe on this layer again. And then after that, you can see here that now we're passing, after the training is done, we're passing in the testing data. And as you can see, there's like a linear trend the probe is able to predict. So the actual intensity values and the predicted intensity values actually match. So as you can see, like on the top right, great job is like a very positive statement. So the actual intensity we set was high, and the model also predicted that, which the model is just learning on the activation. So what this really means is that if there's a simple like linear function mapping, that we can achieve from a layer's activation. That means that this information is actually encoded at the layer at that point. So with Glassbox, you can easily do this with our activation store class and the linear probe class. Now we can move on to the chain of thought.
Cool. So I'll show it. Yes.
Yeah.
Yeah, I think
Yeah.
I'm sharing this one.
Okay, cool. So this next part was on chain of thought faithfulness. So basically when you're like when your model is giving you some answer, often it'll show its chain of thought. Like it'll be like, oh, I'm thinking about this, all to arrive at the answer that it gets to. So basically, to see if the models were actually listening or using that reasoning to actually get its answer, or if it's just coming up with the answer post hoc and just giving like some BS reasoning for how it got there. Yeah, we were interested in, is it actually listening to its reasoning? So we have these two tests. One like a truncation test where basically we loaded these different multiple choice question sets on like science or a bunch of different things, and basically did two different tests where one we cut the reasoning that the model did on what the answer is in half, and we checked did the answer that it had change like by cutting that reasoning in half. And so if it did change, then it was being faithful because it wasn't able to, I guess, look at all of the reasoning. And then we also did an error injection one where basically at the end of the model's reasoning, we would say like, oh, actually the answer is this. So like just changing what it landed on, and then what we found was that sometimes or often, even after saying that, like the model would still give the other answer. So meaning it's not actually listening to like what it's saying, it's reasoning. So we basically would run like all of these questions, and here like this would be like a truncation test where we were seeing if it was being faithful, and no was for no, and for the error injection one it would be yes. So we would pick like a number of questions from any question set to use and run them, and then see what the percentage of the time that they were faithful. So I guess this is like a graph of like the one that I just ran there, where on the truncation test it was 45% faithful, error following it was 25%, and so an average of 35%, meaning that it's only like listening to its reasoning like 35% of the time, which was kind of surprising, to be honest. And it actually varied depending on the size of the model. The larger, like 100 billion parameter models often would like just skip the reasoning if they just knew the answer, especially on the easier questions. So that was really interesting. And then, yeah, basically in our library, we just have these like visualized functions. So after you've run the test, then you can just visualize them with these graphs. So you can also just see like which answers changed when we did the truncation or error injection, and yeah, and then we did I started playing around with like trying to make some like, you know, the 3 blue 1 brown videos where like they like kind of have these cool like visualizations and stuff. It was very early stages of doing it, but like making it so that you could output these as well, where like it would like kind of like show what was going on. But yeah, we can go on to Sparse.
Just a bit of context. So like Manum is a open source library if anybody's interested. If you guys have heard of 3 blue 1 brown, all of his visualizations are made with a library called Manum. So maybe we forgot to mention it like in my part.
Yeah.
But like some of our visualizations, we tried to kind of integrate that to have that cool like 3 blue 1 brown aesthetic, I guess, and then we can move on to sparse auto encodings. Yeah.
Yeah, so another tool that we have in the library is sparse autoencoders. This is mainly based on Anthropic's research. So what sparse autoencoders are is basically, like an example I'd like to give is basically like think of a smoothie. So when you get an activation from an LLM, it's like the vector is very like mixed in. All the neurons have different types of information like mixed into it. So what the sparse autoencoder does is that it expands those. So let's say if the dimension of a vector is 768 in the GPT-2 model, what sparse autoencoder will do is expand this dimension to like 8,000 something. And then after you expand it, you're able to see individual features or patterns that the LLM is able to detect at that point in when you pass the text through it. So what it's basically doing is like if you have a smoothie where banana, strawberry, everything is mixed in, what you're trying to do is basically go back to the ingredients and see which ingredients were used to make the smoothie. So sparse autoencoder does this for LLMs, and it's just a great interpretability tool that we have added to our library. So we have a sparse autoencoder class, and we just have an experiment class which is wrapped over that class. So you can easily run these experiments with sparse autoencoders. So how it works is first step, you have the encoding step where you get the activation again from an LLM, and then let's say the dimension is 768, so it expands it into like 8,192. Again, this is like you can configure it yourself however much you want. And then you have top K sparsity, which is just you want to keep like only like top like 40 or top 50 features out of all those 800 and 8,000 like features that you expand it to. And then once you have that expanded vector, sparse autoencoder is just like a neural network. So what it does is that from that expanded vector, it tries to recreate the original small vector. And the training process is just like getting that error small enough. So once it's small enough, then you have a trained sparse autoencoder, which is able to expand the vector and then reconstruct the original vector. And then after that, you can also save the different features once you've expanded the vector. So all of this is easily done by the sparse autoencoder class and the SAE trainer class. Here's just an example of how you would implement it and use it with our library. And then as you can see for this demo, we're just getting an open web text data set, and we're pulling in different types of data sets for open text, different like thousands of texts, and we're training the sparse autoencoder on it. This is just like the training steps. As you can see, by the end, we get to about like 0.6 or 0.7 variance. What that means is that our autoencoder is able to, from the expanded vector, about like with like 76% accuracy, it's able to reconstruct the original vector, which is pretty good. And then here is just some visualization. As you can see, this is just like the training curve for the SAE. And most of the speed, like in the expanded vector, you want most of the features to be dead and only like the top 48 to be active. So as you can see, most of them are close to zero, and then only some of them are actually active. And this heat map is very interesting. So after you've expanded them, you can save all these features into like a feature atlas and look at for which text these features are getting activated. So you can see like different features on the bottom, and then wherever it's like dark, so like for one column, you can see like three different texts are getting highlighted. So that means those type of sentences are activating this feature. There's like a more better visualization for this. So as you can see, these are some of the top features that after the training that we extracted. So feature number 440 that we extracted, as you can see, the top three sentences are like kind of related to like political stuff. And then you look at feature 578, the top three like sentences that are activating this feature are mostly like NASA landed a spacecraft, a scientist takes a sample of water, space exploration. So you can kind of use this to determine, like the LLM is learning about this specific feature is getting activated from all the NASA related stuff or space or science related stuff. And in the end, again, it's more like political stuff. So the feature 5718 is getting activated from that stuff. So the takeaway is that only 48 of the 8,000 features, 892 features per token get activated, and yet the reconstruction is still pretty high. So we're able to reconstruct the original one. And by getting these features, we're finding like patterns in the LLM that you can actually store and look at. So then you can learn that, this layer is learning this pattern, or this feature is telling us about this pattern, and we can like group them into like things about weather, things about finance, human, and we can save these features into like a feature atlas, which is also another class that we have in the library. But yeah, that's everything about the process.
Yeah, so our next module is the circuit discovery module, which provides data structures that would essentially represent neural network circuits as directed graphs. So these are essentially these are small subnetworks within a model that represent specific behaviors, such as induction heads, which would be like if you had ABC, AB, blank, it would be predicting that. Or you would be doing something like indirect object identification, which you're doing in this example. So this will handle a sentence like when Mary and John went to the store, John gave a drink to blank. So this should ideally predict Mary. And here we are visualizing the circuit graph based on prior research that was done, as you can see here, which has 3 different layers. The first would be the embedding layer. This is essentially taking the sentence and turning it into internal vectors or tokens that the model can read. So essentially just turning these words into numbers. Then we have the attention layer, which is taking these tokens, finding relationships between them, and it would be passing this useful information forward to the next layer, which would be the MLP layer, which stands for multi-layer perceptron. This is essentially like a processing station which would transform and refine this information between the early detection heads and the final output heads, and then give the final prediction. So in this example, you would have the embedding node, which is kind of hidden by the other version, but you would have that embedding node that takes that sentence and it would find these 2 duplicate tokens, which would be for John, which was mentioned twice in the sentence, and it would then pass it to these 2 suppression heads, which would then essentially say it will suppress those tokens and essentially say don't just predict John, and then it would pass it to the MLP layer, which is like the brain that would tell you, which would process that information and give it to the final name mover heads, which would then give the final output as Mary. So what we're trying to show here is that GPT-2 in this example would have 144 heads, but for this specific behavior, just indirect object identification, all you need to show that behavior is just 9 heads and 12 connections just to show that. And yeah, that's pretty much it.
Okay, so start up here and scroll through.
So this part is causal patching. So basically, I'll show you down here where most of it happens. We have the source sentence, Mary and John went to the store, and then a corrupted version of that sentence where instead of giving a drink to Mary, John will give a drink to himself. And so we can target the token Mary, and when we pass through the corrupted run, we can find out what the model was actually predicting here and see if it was indeed Mary. And we go down to this graph, we can see that it's activating over here a lot more than it is over here, which is basically this layer is where a lot of the it says here indirect object identification runs. So where the model is actually looking for the way these things are related. And so we can see it's running on 11. It's trying to, it's connecting Mary a lot with 11 and not so much with any of the other layers. So it is predicting that token that we want it to predict, and making sure, and we can expand this out so that instead of targeting just Mary or something else, we can probe into how the model looks at these different tokens and basically where it will think about them, which is really useful.
So we're just gonna go over a quick integration demo with JSON. I know we're a little bit short on time, but we'll keep it quick and then we'll get into the conclusion of our project.
Discord just crashed.
Crashed.
Oh gosh.
Oh. It's okay, you can start it up. We'll go through our the rest of our slides, unless you got it.
Okay.
You got it?
Open tray.
Okay, we can start our slides and then we'll just come back to it if it starts up. Okay, so I'm not sharing my screen. Oh, yes. Okay, so Jason's gonna show us the integration, if it's gonna work. Nice.
It crashed again. Okay, just skip it.
Okay, no worries. Okay, we'll just, don't worry about it, don't worry about it.
The Discord crashed.
Yeah, it's probably because we have a lot running right now, right?
Yeah, that's fine.
All good. Okay, so I know our presentation was highly technical, but we'll just go over some key achievements to summarize everything. So one of the major achievements that we're really proud of is being able to publish this library so that it's accessible to other students and researchers alike. So it's out there, and it's also in obviously like a experimental phase, like a 0.1 phase. So it'll continue to develop, and our plans for developing, or I guess more achievements. So being able to evolve from reading research to actually building these tools directly based off of the research, that's one of the big ones. And then taking ownership of certain modules. So we tried to build our team in a way that such that each individual would continue down the specific module that they were working on in the beginning of the semester. So they kind of build that type of engineering ownership in that side of the project. Vibe coding skills also, because it's becoming very widely used in industry. Like there's heavy dependence on AI. So trying to integrate that into our project and integrate like automated checking and all that kind of stuff. And then obviously communication for this type of project, since it's highly technical. I'm sure you guys faced it listening to us try and explain these types of things. It's very technical, so being able to kind of summarize it to a new audience and also gaining that skill for interviews is really important. So being able to talk about your projects, etc. And then conclusion and next steps. So a lot of our demos were done using GPT-2 just for the sake of computational efforts on our laptops. But what we'd like to do eventually is to be able to add more experiments and also scale so that we can run Glassbox on larger applications, like bigger models, like the current Claude models or whatever it might be, which are much larger than GPT-2. A lot of the libraries can be scaled up. So for example, Chain of Thought is an easy experiment that you can run on basically any LLM to get that kind of accuracy to see if it's being truthful or not. And just scaling the applications for real world uses, which is more so focused on security and honesty rather than learning what the LLM is made up of. So yeah, and then supporting integration. So we wanted to show our CLI runner, which is basically a way that you can run our library into like any embedded system, basically like an ML ops pipeline within your workflow. So that'd be kind of to support Glassbox being used for like industry purposes if you wanted to have some automated checks on your models. Yeah. And it's of course open source, so like the previous project mentioned, like if you guys have any suggestions or want to contribute, it's going to be open for the summer. And I think that's about it. We'll open it up to Q&A now.
Would the recent source code leak from Anthropic have helped you in any way?
So we're not like that caught up because our project is like from 8 months ago. So it would kind of require a lot of re-scoping to include that kind of stuff. Like, I mean, I'm sure it'd be really cool. But
Unfortunately, that was leaks for Quad Code. It was like the front end agent handling stuff. And when we're all onto like the back end, taking apart the actual large language model the agent is running on. So unfortunately, it wouldn't have given us all too damage aid, but it's still nice to have.
Yeah. I guess it's kind of linked to the stuff that Aaron kind of worked on because it's like external experimentation where you're not directly looking at the attention heads or the values within the model. You're more so looking at its responses. So I guess it could probably be useful in some experiments. So interesting question. Yeah.
Does this project like support other models other than GPT?
For sure, yeah. We have a general class that does anybody else want to answer that?
So unfortunately, I wasn't able to show it, but the runner we created using CLI lets you add any model, and we've also got frameworks for that. It'll download the model for you, it'll load it, so it'll make sure you load it on the right device. So that's all handled. So theoretically, you could run this with any single model you want, as long as it fits on your hardware.
And I think as long as it matches some of the architectural requirements, like the transformer structure and having attention heads and whatnot, yeah. Okay, thank you guys.
So we'll be moving forward to our last demo of the day for the project, Interface AI. Just request that
No, we were way over time.
It's all right. I think students should also cut into us a little bit, but we definitely.
I'll do the session with you.
This is just the live stream.
Yeah, that would be the most, so here's what we actually do.
Okay. Don't worry about it. I think it's just. Yeah, for the boots. Yeah, check on your. Sachin, can you speak? I can't hear anything. I think your mic is on, but that's okay. Okay, now we can hear him, right? I could for a second, but we can hear him.
Perfect.
This is the YouTube stream. Yeah. But you can use this mic. I'll turn this mic on. Can you guys hear him? Yeah, okay. Okay, I'll keep my mic on, and you guys want to. Whenever he starts sharing screen, just click on that screen.
Yeah, we're good.
Where's the speaker?
Right. Okay. Yeah. So the architect. Can we actually scroll up a little bit? Yeah. So the architecture starts with our front end, where we use a Chrome extension. So this is a Chrome Manifest v3, where we have a content script which creates the overlay that we just saw, or like the pop up there. And then we have a background service worker in the front end as well that manages the connection with our backend and with some like external services like Google OAuth. So our main entry point into the backend is with our Flask backend is the main.py file. And then we also have a WebSocket server for like real-time two-way communication between the front end and the back end. And then as well as like the agent session manager, which helps manage the states of the AI LangGraph agent layer. And we'll get to that later as well with the LangGraph agent. And then we also use PostgreSQL for the database to store user profiles, agent memory, and then this helps keep the agent persistent across different user sessions as well. And then each service is in its own Docker container, which helps with independent scaling. And we use GCP with Postgres, and as well as hosting the Gemini LLM model as well. So starting with the front end, so we can see some like initial drafts of the UI of essentially how the agent or how the chat interface was going to look. So we wanted to focus on a lot of like frictionless design, and it should be very intuitive to use, and it also shouldn't really obstruct your website itself. So some initial designs would change the size of the website, and then it would look like some of the other existing alternatives online. But we decided to take a more modern and clean approach where the pop-up is able to like move around, and you're able to close it and reopen it so that it doesn't actually like obscure your website, and that you're able to like close it, do some browser task yourself, and then open it whenever you need to do some like autonomous workflows.
And so Vision AI is basically a secondary way of, for example, getting page tags, for example, or trying to figure out what's on the page for using your automated agents or your content scripts, for example, and then you're trying to navigate the site for these. But what, for example, you have shadow DOMs or some elements there aren't interactable or not accessible. You can't find them through the DOM. Well, this is where Vision AI comes in, where you can use service to basically, it'll take a screenshot of the page and then analyze it using a hybrid of Gemini and EasyOCR to basically detect what's on the screen, and then from there determine what target does it need to find based on the goals. So EasyOCR is basically a character recognition tool where it's strictly for grabbing the XY coordinates of something. So, for example, if we're trying to search for something in Google, let's say we're on the Google homepage and we're trying to search for a certain website. So first thing we need to do, obviously, is we need to find the search bar. usually that's identifiable through a label. For example, we'll have, say, search in the text box, for example. So in those, then we need to find the word search. So how it works is that it will take a screenshot and then it will, in the background, draw a bounding box on that text. And from there, it can execute the action. So click on it, fill in the input, for example, hit enter, for example, things like that. If it's a page that's more complex, that has less text, like say the search option on that page is a magnifying glass, and you can't find that in the DOM, for example, then you can use Gemini that has better conceptual awareness, but it also has better contextual understanding, so semantic understanding that it recognizes, okay, a magnifying glass usually is associated with the search icon, for example. In the background, when you're trying to find something, either it be text or something that may not be identifiable as text on the screen, it'll generate in the background, okay, if I'm trying to find settings, for example, okay, usually that might be associated with a gear or a cog, for example, and you can use that to find it quicker. So the flow is, you'll take a screenshot of the user's tab. It's going to send that image payload to the Python-based microservice, and basically the service is going to evaluate the current goal, and if it routes the image using EasyOCR, well then we only need to get the coordinates because it's just text. That's really easy to do because then we can just grab the coordinates and then don't need to get complex understanding of the UI, for example. And then the service will combine this data and basically return actual UI targets that the agent can physically, for example, move the mouse and click on a panel, for example. So some other alternatives to this were, for example, Grounding Dino, which is very good at image recognition or drawing bounding boxes on certain things you're looking for on the page. And for example, PolyGem, which is a vision language model in GCP as well. The problem with these is that these can be very computational heavy to run, and they can take a long time. The key here is that we need things to be accurate, but we need things to be quick as well. Some tests we ran, for example, with PolyGem, one, again, it can be slow depending on what hardware you're running on, but sometimes it can take like up to 40 seconds to find something on the screen. And obviously, you're not going to be sitting there for 40 seconds trying to find something that's already right in front of you that you could easily click on yourself. We need this to be automated and need this to be, on most cases, quicker than if the user were to manually go through a workflow themselves, trying, for example, navigating to a certain site or going to say, I want to open this show on Netflix, for example. It should be quicker at this flow than no matter what. So making sure that it's quick at identifying things as well as accurate is very key. I guess we can move on. So. long enough, it will usually, it may take a while. I wouldn't waste it. Try the, hard ones. So other than obviously everyone contributing to the project, of course, we had around 172 commits total in the end, which honestly could have been more since a lot of changes we had were very big changes that could have been pushed into subcommits and smaller ones, for example, but we did have a lot of changes, iterations over the past 8 months. Something important is that each team member is responsible for a major feature of the extension. So each of us exclusively developed one part, for example. So I focus on Vision AI, team members and others performance, for example. So when we bring that on our resume or to interviews, we can talk about how we start developing that start to finish, every part of that and how that works, so we can be proud of that. And of course, in general, this is a very typical example of an application or extension that's common or popular in the area of consumer AI, which is very in demand nowadays. So obviously knowing the tech stack used for those, and also obviously being well versed in those language technologies, whatever, that's very valuable nowadays, of course. Any questions?
Yes.
What are some things you guys did to speed it up?
To speed it up.
Well, like for example, like in the beginning, I used like some earlier models of Gemini, like 1.5, for example, where I'd use these VLMs or other LLMs that I had to prioritize or in theory should be quicker or not quicker, but more accurate in determining where an element was on screen, for example. But I found those, for example, this extension shouldn't be so taxing on a laptop, for example. It needs to be very extendable and runnable on lots of hardware, for example. And obviously, I think the problem with Polygemma is that it was very sensitive, where it had a very small threshold for what you're trying to look for. You had to be precise about how big something was on screen that you're looking for. So if it's an icon, like what are the dimensions of it? And then if it was like out of that range, for example, it would just highlight the entire image. So it was very frustrating to work with. So it was kind of a brute force method of just having Easy OCR and Gemini combined together. Because the main strength is that Easy OCR is good for text detection. From testing, semantic understanding in like some cases is okay, but usually it's not the best because sometimes like small icons can be really difficult to find. In the background, like I said, what it does, if it's trying to find an icon, it'll generate some keywords that can give it some ideas to think about what it might look like and what generally it might look like. Yeah, sorry, does that sort of answer your question?
Yes.
I remember seeing right, I'll let them know.
Yeah.
Wait, so I should continue.
That was something I forgot to add, where like depending on your keywords, if you say like search for a go-to, for example, well, depends on like for testing, I was forcing Vision AI to be used completely, so I would want it to try and go find the search bar and then search for it. But if you say like go play a Minecraft video on YouTube, well, you can directly just go to the link with the query already inputted because that's a content script or an action that you can execute just by modifying the URL. So you can go to that directly and do the whole thing in 2 steps versus like 3 or 4, for example. So that was an important key.
Yes.
Yeah, I was gonna say, like, I saw a while back that, like, compared to like a simple like Google search, running like inference on LLM is up to 10 times more energy usage. Something like this, where you have like an entire like reasoning model and you have image processor. What's like the energy usage on something like this compared to an average browsing session?
I mean, I couldn't tell you the specific numbers for that, but I was assuming it's a lot more taxing to do for sure. Yeah, I'm not really well versed in that, to be honest. I'd say in terms of like hardware, yeah, it's definitely a lot harder to run, obviously, than just doing it yourself in the browser. But if it gets to a point where this is like much, much quicker and much more convenient, then that's a trade-off you might want to make, to get things done quicker. All right.
Any other questions? Yeah.
So just to conclude, we're done with the presentation for all of 3 projects. Really great work, I think. They were all so cool. So we'll be having the like set up now, and then we also have like the 3 booths for the project. So if you have any particular kind of questions or like how to join GDG, how to be part of open sources team or any such questions for the leads, you feel free to join the group and talk to them. And then we'll also have a general article if you wanna talk to him about anything. And then as a community lead, feel free to come to this booth and we'll have our newsletters here. So yeah, it's more like an open networking session for now. So thank you guys for coming in and great presentations. Thank you.
Yeah, so just to clarify, GDG booth will be here, so